Thanks to the organizers for inviting me. It's truly a great honor to be here and speak with all of you. So I learned that both Zico and Dom share their ICLR experiences at the beginning of their invited talks. They are clearly much more senior than me, but there's one thing I can say that I have done before them. That is, I have attended the very first ICLR conference in 2013 in Arizona, United States. At that time, I was a first-year graduate student at Stanford University. And this is the very first paper I wrote in grad school with Rachel Socher, Chris Manning, and Andrew Ying. The title is Learning New Facts from Knowledge Bases with Neural Tensor Networks and Semantic Word Vectors. So it's totally normal if you have never heard of this paper, but it was published as a workshop paper at ICLR 2013. In the first ICLR, the conference had only 24 conference papers and 28 workshop papers, and my paper was one of those 28. So it has been 12 years since the very first ICLR, and since I wrote my very first paper in grad school. The world has clearly changed a lot. So over the past decade, I've been mostly publishing in NLP conferences. So today, for me, it feels really special and humble to come back to ICLR, this time speaking in front of thousands of people. This talk will be about language models. And this is what we often think of when we talk about language models in 2025. ChatGPT, Claude, Gemini, DeepSeek, Llama, Qianwen, and many other models. Their capabilities have been improving at a very fast pace. Some of these models are more open than the other models, and some of these models are only accessible through APIs. But the one thing they all have in common is that these models are all developed by industry and large research labs, backed by massive computational resources. So you might wonder, what am I doing here? I'm a 100% academic. What can I possibly tell you about language models? So I went back and forth. And I thought maybe I can tell you the dilemma that many of our academic researchers are facing. As an instructor, I teach a very popular large language model course at Princeton about how language models work. But most of us don't really build language models by ourselves. And to make things even worse, the language model technical reports we read today are very different from the research papers. So to make things even worse, the language model technical report we read today are very different from the research papers we used to teach our graduate students. So I'm not going to tell you where these codes come from, but you can see the wording from these papers. So the technical details are often very vague, imprecise, or just gloss over. Of course, there are still some really great papers. So students have learned a lot from the papers like InstructGPT and the DeepSeek R1. So as researchers, we aim to do fundamental work on language models. But in reality, we are all deeply constrained by compute. In a field that's moving really fast, how can we even make sure that we are making relevant and meaningful contributions? So this is a question I have got from my students all the time. But academia has never lacked smart people. Even if we are not building language models by ourselves, there are still many ways that we can engage with language model research and make a real impact. So one important direction is evaluation, understanding what current models can do and cannot do. A great example is SweetBench, developed by a group of Princeton students and published at ICLR last year. So it evaluates whether language models can perform real-world software engineering tasks, and now it has been adopted by nearly all the frontier labs. So last year, my group has also built this benchmark called ChartArchive, which is a benchmark for understanding charts in scientific papers. Now it's used to evaluate OpenAI's latest models. And this year at ICLR, we are also presenting two benchmark papers, SorryBench for safety refusal and Helmet for long context language models. So feel free to check out these papers. And another important research direction is mechanistic interpretability, trying to reverse engineer what's going on inside language models and to identify model components or circuits that explain model behaviors. So I also have a few students in my group working on this line of research, and it's a very fascinating and growing research area. So more broadly speaking, there are many exciting opportunities for academics, even if you don't train these models yourself. So you can work on agents that build on top of frontier models to solve really challenging tasks. You can work on theoretical analysis, inference techniques, and systems for language models. There is also really a lot of really important problems on safety, policy, and using language models to create impact across other academic disciplines. So at Princeton, I feel very lucky to be surrounded by lots of the amazing colleagues and students working on all these different aspects of the language models. So a few days ago, ICLR just announced outstanding papers at the beginning of this conference. So this year, 2 out of the 6 awards are actually given to Princeton students. And all the 3 outstanding papers are academic language model papers. So I guess I don't really need to try very hard to justify why these topics are important and relevant, or how amazing our Princeton students are. Now I want to come back to this hard question. Should we still train language models on an academic budget? So this is a question I've been thinking a lot over the past 2 or 3 years. Okay, so why does it still matter? So I deeply believe that academia still has a role to play. So first, we need to understand what works and what doesn't. There are so many moving pieces in the entire training pipeline of language models: data, model architecture, training algorithms, optimization, and more. And for many of them, we still don't have a very deep understanding yet. So we can bring openness and scientific rigor and write good papers by carefully documenting what we do and sharing the insights with the community. And I also believe that academics can develop novel and compute-efficient solutions for training better language models. And we can contribute great open models that is reproducible and useful for the broader research community. So if you, like me, believe in the importance of training language models in academia, we still have to face reality and work around our academic constraints. So it's very likely that we can only work with small-scale experiments. And how do we know whether the insights from the small models or small data sets actually generalize to larger-scale settings? Another question we have been always asking is that even possible to meaningfully engage with state-of-the-art models, or at least the best models in the open space? And we have to rely on public data sets and the infrastructure for training these language models. Are they really good enough to support our training runs? And another reality we have to face is academic teams are usually very small. I have a group of 8 PhD students. Should I ask all my PhD students to team up to train language models? And how can they make sure that they are still able to finish strong and independent PhD dissertations at the end when they graduate? And finally, a fundamental question we have to figure out is what it even counts as a meaningful training compute budget in academia. So people often say that constraints drive creativity. So let me just show you a concrete example. So back in 2021, my group started thinking about pre-training language models. At the time, it's basically bird-sized models. At the time, we basically didn't have really we had very little GPU access. And this plot from weights and biases is actually one of our training curves at the time. So you will notice all these like colorful segments from this kind of training run. So each of these segments is actually represents 1 hour training job. So my students came up with this very clever idea. If there is one free GPU in our department that no other students want to use, so they will just get it, this one single GPU to train for 1 hour, especially in the evening time when no students really want to run interactive jobs. So this was actually allowed under our scheduling system. So over the time, they accumulated enough of these 1 hour experiments to actually finish training a BERT model. So now we call this at Princeton as 1 hour job trick. And I want to give the credit to my student Tianyu for inventing this idea. So before I dive into the main content of this talk, I want to come back to this slide and discuss what I mean by an academic budget, since the resources can vary a lot across different universities. So for the rest of this talk, I will assume a budget which is 100 to 1,000 GPU hours, A100 or H100 GPU hours for running the main experiments. So what does this number mean? So it means that if you have 8 GPUs, so the main training runs will take from half day to 1 week. So it also means that, so this is a really rough calculation. It also means that this accounts for 0.001% of the compute used to train a frontier model. To be honest, I don't know if this calculation is correct because it's calculated by ChatGPT, and we don't really know how much compute is actually needed to train the frontier models. But my point here is, what I mean by the academic budget here is really, really a tiny fraction of the industry level compute. Also, I want to say that I completely understand, even this level of compute is still out of reach for many university labs. And I will return to this issue at the end of my talk and discuss that we need more GPU support in academia if we want to be really meaningfully engaged with language model training. Okay, so for the rest of this talk, I will focus on 3 research areas where I believe the academic researchers can make meaningful contributions, even with limited computational resources. So these 3 areas are small language models, data curation, and the post-training on top of open weight models. My group has been exploring these topics in all these 3 areas. So I would like to share some of our work, along with a few stories and the lessons we have learned during this journey. So let's start with small language models. So the definition of small language models is still evolving. I believe by today's standards, we usually think of small language models as models with 1 to 10 billion parameters. So why do we want to work on small language models? Well, for obvious reasons, we simply cannot afford to train large language models. But what surprised me most is small language models actually have emerged as a research direction in the past 2 years. And the people have been actually starting to use this term, ACLMs. So we like small language models because they are much easier to run, much easier to fine-tune, and they are better suited for on-device or edge applications. So if you look at the downloads of the Llama 3 models, the 3 billion model and the 8 billion models have far more downloads than the 70 billion models. So my group started to think about training small language models about 2 years ago. And at that time, models like GPT-3 or Google's PaLM models all have hundreds of billions of parameters. Then in early 2023, Llama 1 came out, and the Meta released a series of models, the Llama 1 model of different sizes. And the exciting news at that time was a 13 billion parameter Llama 1 model already outperformed a 175 billion GPT-3 model. Then we started to think about, maybe we can, in academia, maybe we can even create an even smaller model, such as like 1 billion or 3 billion models, parameter models. And then we did the calculation quickly. And we quickly realized that this is also not possible to do at all in academia, Since training a 3 billion model on 1 trillion tokens takes around 30,000 GPU hours, and this is way beyond the resources we have. So we have to come up with better ideas to work around our constraints. So this has eventually led to a project we called Sheer Llama, which was actually published at ICLR last year. So the key idea here is very simple. So instead of training a 3 billion model from scratch, let's start from a larger pre-trained model, such as Llama 7 billion model, and let's start from there and try to produce a 3 billion model. So we first try to reuse a subnetwork from the 7 billion. Okay. So we first try to reuse a subnetwork from the 7 billion model. And this can be done using techniques from structure pruning. Then in the second step, we continue pre-training this pruned 3 billion model and to get the final model. So I should mention that the structure pruning is actually a very cheap step. We only use 1% of compute for doing the structure pruning, and the remaining 99% compute will be used for continued pre-training. So more concretely, here our goal is to produce a 3 billion model from a 7 billion model with a targeted architecture. So here we have a targeted architecture. For example, here we define the architecture of 32 layers, 20 heads, and a hidden dimension of 2,560. So we can prune this model architecture from the source model by removing the heads and the intermediate dimensions to match the final architecture. So this eventually actually becomes a constraint optimization problem. So we can model each pruning decision as a masking variable, and then we can use Lagrangian multipliers to enforce the architectural constraints. So the result of this pruned model will be exactly match the target architecture that we actually want to get at the beginning. At the beginning of this training, so this model will be exactly just as if we had trained this 3 billion model from scratch. So this all sounds very promising, but one crucial aspect we have not discussed here is what data we should pre-train to use to pre-train this 3 billion model. So thanks to the open source community, at that time, Together released the Red Pajama, which was an open replication effort of the Llama pre-training corpus. The dataset includes subsets from Common Core, GitHub, books, archive, and a few other domains. And each of these domains comes with very different domain proportions. So the next question is, given we already have such a clean pre-training dataset, should we just sample from this off-the-shelf pre-training dataset? The answer is no, because we found that the loss difference across different domains compared to training a 3 billion model from scratch are highly imbalanced. The loss difference on C4 subset is much higher than that on the GitHub. So in this work, we figured out actually a clever solution, which is the idea here is we can actually leverage the larger series of the Llama models to fit the scaling laws. And then we can use the scaling law to predict the reference loss across different domains for this smaller 3 billion model. And then we can use this reference loss to help us adjust the domain mixtures. And this turns out to work really well. And it has led to significantly better downstream task performance compared to sampling from the original proportions. So this was really a cute academic research project. And I have never expected this project to go this far. So by the time that we wrap up this project, Llama 2 models were released. And my students have really tried very hard to pull off this project by pulling together the compute resources they can find at the time. So eventually we end up using the Llama 2 7 billion model to produce 1 billion sheer Llama model and another 3 billion sheer Llama model. So these models were actually only trained on 50 billion tokens, using only a few hundred GPU hours. That's basically pretty much 3% of compute it would take to pre-train these models from scratch. So if you do the calculations, this basically also means that if you have 8 GPUs, all these training runs can be done using only 2 or 3 days. So when we released these models, I was very surprised that this sheer llama 1 billion 3 million models turn out to be the state of the art among 1 billion 3 billion models, outperforming many other models that have been trained on much, much more data. And it turns out that people really like these small sheer llama models. So we released our sheer llama model, 1 billion 3 million models on Hugging Face. And they have received over 800,000 downloads in just a few months. And another interesting fact is the 1 billion model has been actually 10 times more popular than the 3 billion models. And there are a lot of useful practical use cases for the models at the 1 billion model scale. And we did this work in late 2023. And in 2024, we have seen a clear trend in industry using a similar idea of producing small language models from the larger models, including NVIDIA's miniature models and the Meta's Llama 3.2 models. And this figure is from the Llama 3.2 release. As I highlighted here, the 1 billion 3 billion models were both pruned from the larger 8 billion and the 70 billion models of Llama 3.1 before they actually do the continued pre-training. So today, sheer llama is definitely not state of the art anymore. But the progress of small language models in the past year has been really, really amazing. So this figure shows the model sizes needed to achieve an MLU score of 65 has steadily decreased from like a few years ago, from the 70 billion model, the Chichima models, down to the Chen 3 billion models. So these models have really benefited a lot of people in both academia and industry. However, I should also note that the best effort today, like Chen 2.5, 3 billion model, was actually way overtrained. It was trained on 18 trillion tokens. So that's actually still far beyond the academic budgets that I just talked about. So what's next about small language models? So besides using pruning and distillation to compress larger models, a really interesting question is, how can we train small language models with much less data? So I talked earlier about using larger models to help us adjust domain mixtures. But another exciting direction is to use large language models to generate high quality synthetic data to help us train the small language models. This idea has been explored in recent works like Microsoft 5 models and Hugging Face small LLM models. But there's still a lot of open research questions in the open space that we don't fully understand yet. And from a scientific perspective, I also think this family of small language models itself is actually already very interesting. So we still lack a deep understanding of the fundamental properties and the capacity limits of these small language models, especially when these models are trained on very, very large or highly synthetic data sets. These are all the open questions that I think are still worth exploring next. Okay, so next, I'm going to switch to another area that is we have been really passionate about. That's the data curation for language model training. So here I'm going to mainly focus on pre-training data. And I think it's actually one of the overlooked opportunities for academic research. So why should we work on pre-training data? So clearly the quality of pre-training data really impacts the performance of language models. So these days, most language models are pre-trained on massive web data, but this data is often unstructured and poorly understood. So for a very long time, data curation has been seen as more or less of engineering task rather than a research problem. But I think that is actually changing and be going to change very soon. So the other question is, should academic researchers work on pre-training data? So my answer is yes. I personally believe that I personally believe that this is actually one of the most promising directions, where the small-scale experiments can actually transfer to the larger settings. Of course, I cannot say this with 100% confidence, but there is this very nice work from the data comp LLM competition, which shows that the data sets tend to rank consistently across the scales. Okay, so now let's do a quick reality check. What should be a reasonable setup for doing the pre-training data research in academia? So right now, the common practice here is to train 1 billion models on 30 billion tokens, which takes about 8 GPUs to train for less than 1 day. So this still is within what I would consider as an academic budget that I defined early. So in the past 2 years, we have seen several significant efforts in curating pre-training datasets in the open space. So I already mentioned Red Pajama, which was released by Together in early 2023. Later in 2023, AI2 also released DOMA. This dataset is used to train their OMO models. So this pre-training corpora often includes subsets from the large web crawls like Common Crawl, along with more curated data sources like Wikipedia, books, and academic papers. And last year, the data comp team across many institutions and companies launched the data comp LLM competition in search of the next generation of training data sets for language models. The DCL LLM pool here is 100% composed of the Common Crawl data, and the pool sizes are much larger than the previous data sets. So we should really thank all of these open efforts, which significantly lower the barrier for pre-training data set research in academia. So the rest of the community is able to push research forward in meaningful ways. Okay, so let's come back to the research questions. Now we have relatively clean pre-training data sets. So what kind of research questions can we even ask about the pre-training data? So one important direction here is quality filtering. So how can we even measure the quality of pre-training data? And how can we select the data according to these quality signals? And a recent emerging trend is called model-based quality filtering. So can we actually even leverage language models to provide signals to decide data quality? There have been already several efforts in this direction, including Google's Ask LLM, Hugging Face FineWeb EDU, and what I already mentioned about the DCLM baseline. And I expect that we'll see a lot of similar efforts happening in this space. So last year at ICML, we presented this work called curating. The key idea here is very simple. We use language models to help us assess the quality of text through the pairwise comparisons. So we define the quality along the 4 axes: writing style, facts and trivial, educational value, and the required expertise. So essentially, we developed a framework that compares any 2 pieces of text in the pre-training corpora on each of these 4 dimensions. And then we aggregate these language model judgments into quality ratings for individual documents. And this approach has worked really well. And by assigning quality ratings to the individual documents, we actually now have a very powerful tool for understanding what is actually in the pre-training data and how the document quality varies across different domains. As a figure you can see from this slide, the archive papers tend to score much higher than other domains on the required expertise. And the Wikipedia contains the most facts and the trivial. But the quality of individual documents within each domain still varies a lot. So this is a very nice starting point. But the next bigger question here we want to ask here is, so here still we try to analyze all these kind of curated domains like Wikipedia or archive papers. But how can we even make sense of the massive unstructured web data like Common Crawl? So this year, we put a lot of effort into trying to better understand the web data. And the one project I'm really excited about is called Web Organizer. This is a collaborative project with AI too. But I should really emphasize that this project is really an academic budget project that a lot of people can do in the university labs. So the key result here is we can actually now partition massive web data into these very interpretable domains. So in Web Organizer, we build a rich two-dimensional structure for pre-training data by introducing two complementary domain taxonomies, topic and format. Topic and format, which classify web documents into these categories based on the subject matter and the style. So we use language model annotations to help train the domain classifiers. And the visualizations here clearly show how the common crawl data actually looks like. So as you can see from these visualizations, so web data is actually pretty balanced across many different topics. But there is a clear skew towards a certain formats. So we actually find that the common crawl data actually contains a lot of the pre-training documents from actually like personal blogs and the product page in the pre-training data. I think it's likely because this figure is too big. Okay, let's continue. Okay, so this all looks really nice. But the natural next question is, if we are able to partition the web data into all these kind of different partitions and domains, how can we actually use these partitions to create better data sets for training language models? So one approach here is to optimize domain mixtures. So we use a framework called RegMix, which is also a paper that is actually presented at ICLR this year. So the idea here is to sample a large number of random domain mixtures, and then we can train a lot of small proxy models. Here, we simply just use 50 million parameter models trained on just 1 billion tokens. And then we can fit a regression model to predict the downstream task performance based on the different domain mixtures. So this gives us actually a very effective way to search for better mixtures that can be later used for training larger models. So the impact of a domain mixture is actually quite significant. As I mentioned earlier, all of these experiments were done at the 1 billion model scale with 29 billion training tokens. So compared to just doing the uniform sampling from the common crawl data, the optimized domain mixtures based on either the topic or file format already improve the performance quite a bit. So here we basically measure the average performance on the 9 downstream tasks. And if you can combine the topic and the format, so you can work even better. And this result is already quite comparable to a very strong quality filter, basically the FineWeb EDU from Hugging Face. And if we can combine the quality filters and the domain mixtures, we can actually get the best result overall. So compared to the uniform sampling, the average downstream task performance is increased from 51.6 to 56.2. I think this is actually a pretty large gain at this scale, 1 billion model scale. So I think this really highlights the importance of curating better pre-training data. There are still a lot of things that you can discover from the pre-training data to train these models. So one last thing I want to mention is that these domain partitions can also help us understand what quality filters are actually doing. So here you can see that the optimized domain mixtures we have learned already look very different from the natural distribution of the common crawl pre-training data. For example, these domain mixtures tend to actually use more science and technology documents, and also more tutorial and academic writing papers for training language models. And then if we compare this to the domain distributions from the existing quality filters, like FineWeb EDU and the DCLM baseline, we can clearly see that where these domain these quality filters actually prioritize or underrepresent certain types of content for training language models. So this gives us a very interpretable way to analyze and compare different data selection methods. So finally, I want to briefly mention another project we work on. So my group has been very interested in long context models. And this is probably also the most compute-intensive project we have done so far. This actually takes 10 times more than the compute budget I actually mentioned earlier. So this is what we did. So we have developed a 8 billion long context model called ProLong, stands for Princeton Long Context Models, that can support 12,000 context lengths. So since we cannot train a model from scratch, we start from the Llama 3 8 billion model, which only support 8,000 context lengths. And then we do continue pre-training on top of this model for 40 billion tokens to gradually increase the context window size from the 8,000 context size to 512,000 context size. So by the time that we wrap up this project, so Llama 3.1 just came out. And it turns out they actually used 800 billion tokens for their long context pre-training. So we only used 5% of their compute. But we found out that we evaluate our model with the Llama 3.1 model and many other open models, open long context models. And it turns out that we can still match their performance on long context evaluation. And the ProLong also outperform many other open models under 10 billion parameters. So we must have done something correct here, right? So what is the key finding here? So the answer here, again, is in the data. So we actually find that if we can find a strong mix of the high-quality long context data, which is basically code and books, along with high-quality short context data, this will be really, really critical for the long context task performance. So if you're curious about the full details, feel free to check out our paper. But this result really shows that there's still a lot to be discovered about pre-training data that we don't fully understand yet. So I have shown a few works that we have done in my research group, and the positive results we have learned so far. So personally, I feel like we have just only started to scratch the surface when it comes to understanding and improving the pre-training data. So over the past year, more and more people have started to recognize how critical the pre-training data is. And they have proposed a lot of really creative and promising ideas. So I have listed a few papers here I personally really liked. Some of these papers are also presented at ICLR this year. So one thing they have in common is that these are all academic papers operating within academic budgets. So I really believe that it's totally possible to do impactful and original pre-training data work in academia. So let me wrap up this part. So what have we learned so far? Honestly, I think our understanding of pre-training data is still quite limited. Despite recent progress, we're still operating with pretty primitive tools, and there's still a lot we just don't know. There are many open research questions remaining, and how can we approach data curation from the first principles, and how can we do so in a way that is actually efficient? Efficiency is also a really important aspect we have to think about in turn when it comes to pre-training data research. And I believe this is one of the most foundational models in developing language models because it affects everything else downstream. And to finally, one big question I found really fascinating is how does the data quality actually interact with the scaling laws that we have been talking about all the time? Okay, so finally, I want to talk about the third research area that I've been really interested in, that is the post-training that built on top of the open weight models. So I don't need to really spend too much time on this part, because this is really probably the most obvious and active research area for academic research right now. There is already really a lot of the amazing work happening in this space. So why should we work on post-training? So clearly it's much cheaper and much more computational feasible. And also thanks to the release of all these strong open weight small language models, we are now able to build really good models that are better aligned with human preferences or that specialize in specific capabilities like coding or reasoning. So compared to pre-training, which has kind of settled in a fixed pipeline, post-training is still changing very fast. There are lots of really exciting research opportunities, both in data and algorithms. So this includes instruction tuning, reinforced learning from human feedback, preference optimization, and most recently, reinforced learning for reasoning, which might be the hottest topic at this conference. So since there are so many things you can work on in post-training, so for the rest of this part, I will just zoom in and share one thing I have really learned over the past year. So this is about preference optimization. So we start from the preference data, which is basically in this format of the triples or prompt and the winning response and the losing response. For example, given the prompt, what is the official mascot of Princeton University? A winning response might be the official mascot is a tiger symbolizing Princeton's fierce spirit. And the losing response might be the official mascot is a white squirrel. So the goal here of the preference optimization is to continue fine-tuning the model on top of the preference data that can assign a higher probability to the winning response than the losing one, given the same prompt. And a lot of early work in this space used RLHF. But thanks to the direct preference optimization DPO paper from Stanford University in 2023, a lot of research focus has shifted to offline preference optimization. So instead of learning a reward model and running reinforcement learning, DPO directly optimizes this objective on the preference data by comparing the current model to a reference model before training. So I have to say that DPO has been really a major win for academic research. It's such a simple method, works really well, and it doesn't require reinforcement learning to make it work. So last year, my group also looked at this problem, and we proposed an even simpler training objective for preference optimization called SIMPLE, which was published at New York last year. So our starting point was to understand why DPO works. So we actually noticed a discrepancy between DPO's reward formulation and how generation is actually done during the inference time. And this issue was also observed by another concurrent work actually from Cho's group at New York University at the time, which found that DPO really flips incorrect rankings during the training. So this made us start to think about whether DPO is the right training objective and what is the role of this reference model. So in SIMPLE, we just made a very simple change. Basically, we removed this reference model from the reward formulation, and then we added a length normalization term to avoid the length biases. Then we can just simply plug in this new reward formulation into the Bradley-Terry ranking objective. So this slide shows a direct comparison between DPO and SIMPLE objectives. So in our final formulation, we also added a margin term to encourage a larger gap between the winning and losing responses. So in the paper, you can find a lot of derivations and analysis for why we derive this objective. But here is actually not the main point of my story. So SIMPLE is really just such a typical academic machine learning paper, right? So we designed a new training objective, and then we need to show how it works compared to DPO and many other preference optimization methods. But what is really interesting here is, so this post-training is such a fast-moving field. There was no clear consensus on how we should evaluate these methods, including which models we should run, which preference data set we should use, and which evals we can actually trust. So our team has spent a lot of efforts just trying to get this experiment correct. So we decided to follow the best practice at the time. So for models, we used the Llama 3 and the Mistral model. This is basically the state-of-the-art small language models we could run at the time. And then for the evaluation, we started with alpha eval 2 and empty bench. We found some issues in these evaluations, and then we moved to arena hard and wild bench. Eventually, we decided to actually rely on the chatbot arena, which use the real user votes to judge the model performance. So even after fixing these models and the evals, there are still many different training pipelines that you can consider for comparing the different post-training methods. So here we consider two training pipelines. The first training pipeline we call the base setting. So basically we start from a pre-trained Llama 3 based model, like for example, Llama 3 based model. And then we do the ACFT by ourselves. And then we do the preference optimization on another open preference data set. So this is basically the full pipeline that basically you need to build the entire post-training pipeline from a pre-trained model. And then we also have another instruct setting. So we start from an instruction-tuned model that has already gone through the post-training, like closed-form RLHF. And then we need to use it. So we use this to actually generate the own policy preference data labeled using an external reward model. So why am I telling all these details at such a big conference keynote? Actually, my point here is there's really no easy eval for language models, especially for the open-ended task. There are actually many design choices or evaluation choices you can make in the post-training pipeline. And my advice here is basically just try to follow the best open source efforts. At least we can actually make sure that the results are actually convincing and also meaningful to the community. So this is basically what we did. So we compared simple and DPO across all these settings. And then we found that simple consistently outperformed DPO. In some settings, the games are larger, and in some other settings, the games are smaller. But what surprised me most is, so because students have spent so much time on running the experiments, during this extensive experiment process, the students actually discovered a really strong training pipeline. So to actually produce a very strong chat model. So eventually they actually started from the Gemma 2 9B instruction tuned model. Basically, this is the instruct setting I just described. And they only used the 50,000 prompts from the actual feedback data set to regenerate an own policy preference data. Basically, for each prompt, we sample 5 responses. Then we use a stronger reward model to pick the winning and the losing responses. Okay, so the resulting model here is called Gemma 2 9B instruction tuned simple model. And this process was actually extremely lightweight. It only took less than 2 hours to run on 8 GPUs. And the result was quite surprising. So when we deployed this model on chatbot arena, it immediately bumped the original Gemma 2 9 billion model from the rank of 49 to rank of 31. That is basically an 18 position jump. This model turned out to be actually many other open models and became the strongest sub 10 billion model on chatbot arena and all the other chat evaluation benchmarks. And it also received 1.2 million downloads in just 9 months. So I was also excited to see the people on Twitter call it out as a great win for open models. So what have we learned from this project? And what should we think about next? So there are clearly lots of exciting opportunities for further improving the model capabilities, even for models that have already gone through the post-training, like the simple example I just showed. But I also want to raise a concern here that I think is often overlooked by the community. That is, most of the post-training research today builds on open weight models. And the researchers usually pick like an arbitrary set of the base models, usually the state-of-the-art models that they can run at that time. But what if the different base models give you very different results? So how can we draw reliable conclusions? So let me give you 2 quick examples here. The first example is, we noticed that during our simple project, if we run simple on top of the Llama 3 versus Gemma 2 models, we actually saw very different trends in catastrophic forgetting. And we still don't have a very good explanation about this yet. And the second example is actually related to a very popular topic. So these days, a lot of people have been doing the reinforcement learning for reasoning. So why does everyone start from the Chen 2.5 base model? Why not the instruct model? And why not the Llama 3 model? So these are all really important questions. And we can only answer these questions if we actually understand what went into the model's pre-training process or early stages of the post-training. That's why I actually believe that we need more holistic and controlled studies that actually carefully consider the interplay between base models, training data, reward model, and the evaluation. And I also believe there's still a very, very long way to go for us to really truly understand the impact of pre-training data on post-training. So before I wrap up this part, I just want to quickly highlight that I think it's actually a really exciting time to work on reinforcement learning for reasoning in very favorable domains. So at Princeton, we have a very big team effort focused on formal reasoning in proof assistants such as Lean. So this project called Godot Proval, and we have already developed a state-of-the-art model in formal proof generation. And currently we are actively working on this direction to further push the frontier of this kind of research. And I actually believe this is one of the places where post-training can make a huge impact in the coming years. Okay, so let me wrap up my talk. So throughout this talk, I've been trying really hard to convince you that with just a few hundred GPU hours, we can do serious language model training research in academia. Occasionally, we can even build best-in-class models, like the examples I have talked about in this talk, such as Sheer Llama, Prolong, and Simple. These models coming out from my lab, but they're only built using a fraction of the compute. So even if we are not building state-of-the-art models, I believe that we are at least contributing valuable know-how to this public sphere by running carefully controlled experiments and by writing good papers. So this has been really what motivated me to do such kind of academic language model research over the last few years. So I truly hope that there are more people in academia that can join this kind of effort of language model training. Because if we can share the infrastructure, data, model checkpoints, and the research insights, we will make more progress and build better models. So the research directions I have covered today, the small models, data curation, and the post-training, are all relatively established in the last few years. But the best part about academia is that it encourages a lot of the more bold and unconventional ideas. So maybe the next generation of language models will not use transformers. And we have already seen very promising alternatives architectures out there. Maybe we will not need to rely on next token prediction as the only training objective. Or pre-training on massive web data. Maybe we can train on complete synthetic data to actually make the training even better. And maybe there are better ways to scale the current language models beyond just the model parameters and the training tokens. Academia is the right place to ask this question. But here there is a dilemma. So we don't have resources to scale up these bold ideas. Even if I get something working at small scale, who is going to get to validate whether it still works when these models are scaled up? Honestly, I don't have an answer to this question. I will just give you one concrete example. So this is actually one of my favorite research topics, retrieval augmented language models. But I decided not to talk about it much today during this talk. So over the years, many of us have been thinking very hard about how to co-train the retrieval systems and the language models to build models that can actually truly use retrieval as part of their model architecture. But this is technically really hard. So because updating both the language model and the retrieval data store during training is very, very expensive. And a while back, we did this paper called Training Language Models with Memory Augmentation. This paper still remains as one of my personal favorites. So it's very likely that very few of you have heard of this paper. At that time, we tried really hard, 3 years ago, we tried really hard to train such a family of retrieval augmented language models by changing the training objective and change the way that we actually use the pre-training data. It's a great academic project, and it worked pretty well at a small scale. But at that time, we only had the resources to train a 200 million parameter language model and never had the resources to scale up. So this probably has happened to many research projects. And the good ideas never had a chance to actually fully scale. But over the years, I feel this is totally fine. These ideas we planned in this smaller-ish academic research projects are always still there. And sometimes they may even eventually shape the future work in the ways that we actually don't really know. Okay, so at the end of this talk, I want to return to a more grounded and a realistic question. So in this talk, I'm trying to show you that these research projects can be done in an academic budget. But a very realistic question is, what if I still don't even have access to even 4 or 8 GPUs? This is a very hard and very real question. And probably the situation for many academic labs, especially at smaller institutions or in under-resourced regions. So I want to be clear, this talk is not really about how already privileged groups can do more. It's really about how we can make this kind of research more broadly accessible. First, we don't all need to train language models. There are still many, many exciting opportunities for language model research, as I outlined at the beginning of this talk. And there are also a lot of things we can do at the institution level. And maybe we can do things in a more collective way via cluster sharing, pooled usage, or cross-lab scheduling. So at Princeton, several assistant students in Professor Kiley's group have been working on this co-scheduler for multi-tenant clusters, which helps monitor the underutilized GPU resources on campus and smartly co-schedule lightweight jobs alongside the existing ones. So this is still early work in progress, but I expect this can help institutions stretch limited compute further. So more broadly, I'm really hoping to see new models for collaboration, whether through cross-institution efforts or academia industry partnerships. So while I was preparing for this talk, so I learned a lot from my friend Siva Reddy about how GPU collaborations are actually structured in the European countries and in Canada. They're really making a lot of efforts to pull substantial GPU resources from the different universities and institutions to support a wide range of students and researchers, making this GPU access more equitable and scalable. So in the US, we see a few large-scale initiatives, but still most access still remains very fragmented. Honestly, I still don't have a very clear picture about how things work in many other countries. But I believe that we can actually learn from each other, and that shared infrastructure, if we can do it right, can make it possible for more academics to pursue fundamental large language model research. Just like many of the examples I've shown in this talk, sometimes what we really need is just a bunch of one-hour jobs to get meaningful work done. So I also hope to see more industry programs that support academic research. So my lab has benefited a lot from this program, Microsoft program called Accelerating Foundation Models Research Program. And I know many of my academic friends in the US have been using the GPU resources provided through NVIDIA's academic grant program. So this kind of initiatives can make a real difference, especially for those of us who don't have institutional access to large-scale compute. Okay, so I will just end my talk here. So please let us, academics, help build the next generation of language models. So we may not be able to train the frontier models, but we can still write good papers and build useful and open models. And I believe there's still a lot we can contribute. So I want to thank you all for listening, and I'm happy to take more questions. And I'm sorry about the technical issues. Yeah.
Hi, Danqi. That was a really nice talk. It makes me think a lot. But I have to push back a bit, I feel like, is it really that we want to have the, let's say, limited amount of the funding available to buy all those GPUs from NVIDIA, it's all NVIDIA, so that everyone works on these language models that are actually already products at the academia? Feels like that's exactly the opposite of what we need to do, right?
Sorry, can you just repeat the question? Like,
Oh.
I still don't see you. Where
Oh, yeah.
I see. Okay, sorry about that.
Yeah, I mean, you advocated for the, let's say, diversity in the ideas in academia. That sounds great. But also at the same time, you said that we should support academia with much more GPUs. Now, obviously, we have a limited amount of the funding in the whole society, as we are seeing with the fiasco in the US now. And if we actually decided to put all those monies to buy GPUs from NVIDIA so that the people are going to work on language models in academia when the language models are just products, I feel like this should be done by companies who actually make money out of these language models. And maybe the money can be used better, right? What do you think?
Okay, thanks for your question. So my first argument is I believe there's still a lot of academic fundamental research questions we should ask about language models. In order to answer these questions, we need GPU support. Second, the question is, so many companies already buying a lots of GPUs. So the question is more like whether you should really use all the GPU resources to really do one single run for like products, as you said, or we should actually maybe spare like a fraction of the GPU compute to support this kind of fundamental research. So we are able to maybe come up with better solutions for training these models.
Thanks.
That's the answer here.
I think he's first.
Oh, yeah. Thank you for a nice talk, and I'm here, and I'm undergraduate student from Peking University, and I'm really curious about the questions in your slides. But I want to ask, can you imagine the endpoint of small language models if all the problems in your slides have been solved? Yeah.
The endpoint of small language models.
Yes.
I think this is definitely still an open question. I was really fascinated by the progress of small language models, but still the small language models are not as strong as the larger models because there is definitely still like a capacity limit. So right now, a lot of people are trying to think about whether we should really try to pack all the knowledge into the small language models. All these models can be actually very good reasoners. There have been a lot of questions, but I think the small language models, we can further push the frontier of the small language models, but eventually I don't think these models will still match the performance of larger models, if that's an answer for you. Yeah.
Okay, thank you.
And may I have an...
Yeah, thanks for the very clear and quite entertaining talk. It's not my area, but I sort of in academia for a couple of decades, but my feeling usually is that academia is usually asked for blue sky design towards approach to a certain question. But it's, of course, in your talk, I see a lot of example that constraint, or we just call it reality check, actually promote creativity. But I always get this question in my mind. Suppose I have unlimited access to the GPU. How would I approach this large language model differently from today? I'm just wondering, do you see the academia has any, what's your thoughts about along this line? Instead of asking, what can we do if we only have hundreds of GPU hours, but rather if we have unbounded GPU hours, what can we do differently? Thank you.
Thank you for your question. Yeah, I made it very clear in this talk that I talk about the three research areas is because these are things that we can do on the academic budget that we know that they will likely succeed if we make it work. But at the end of the talk, I also talk about the bold and unconventional ideas, think about model architecture, think about different ways of scaling, and think about maybe generating data. I would say if we have unlimited compute, these are the things that we should really go for it. We should really try to come up with very different ways, fundamentally different ways of training these models. But really the reality is, usually we can only validate. There's still really lots of great academic papers trying to do these things. But the reality is that we just can only validate these things at a small scale, that we don't really know whether things work at a larger scale yet.
Okay, thank
Thank
you.
you.
Mike, I'm here. And my question is also about scaling stuff. And I'm a PhD student in university, and I currently work as an intern in industry, and feel like everything is about the scaling the data, scaling the model size, and most of the influential work is about scaling. And my research area is about post training. So I'm wondering if the academia should also do the scaling stuff, because there are many influential papers and products about scaling, but academia, it is really hard for academia to do the as scaling as the industry. So as a student, I find it hard to choose the role to select which topic should I do for the post training.
Yeah, thanks for your question. So first, I would believe that post-training is probably the area that you can actually easier to do more scaling work compared to pre-training. So my philosophy is like, I think we should first try to, you should come up with ideas, but we should try to first validate this in a smaller setting, and then really try to work around the realistic the compute you actually have, and to figure out what level of the compute you can actually scale up to. And I also think that it's good to really encourage more academia and industry collaboration. So we have the role of academia is always to come up with ideas. Then we can talk with industry people and see whether they are willing to scale up these approaches or not.
I have a follow-up question. Yeah. When things become scaling, some difficult problem there are very easy solutions to some very difficult problem if we have the limit in case we have the limited resources. But if we can scaling, this problem can be really easy. So maybe it would be difficult to just validating in the limited resources.
Yeah, I would say we should try to get more evidence in terms of what methods that work well on the small scale will actually transfer to larger scale. But for some solutions, maybe there's a really difference between small setting and larger settings. Yeah. Then we need to think carefully whether we should pursue this in the smaller settings or not. But I'll talk about the small language model at the beginning. So it's still small models. Maybe the behavior is actually very different from large models, but still these models itself are actually very, very helpful, very useful to run and to do a lot of things.
Thank you.
Hello. Thank you for the talk. It's really wonderful. And my question hinges on the collaboration of smaller models. My view is that the smaller models helps, particularly if they can collaborate it well and have a chance to be the larger model. But it doesn't seem to be true in the industry. The industry still use large language for these agentic workflows. So I wonder what's your insights, like why we still haven't done this collaboration team of smaller models and to actually bring this language model out of lab to real life applications?
First, I would say the small language models have been already very useful. If you just look at the downloads, so many people are using the small language models for the adaptation and also the edge applications. But you talk about the collaborations between small language models. I have never done work in that space, but I have seen very interesting work, for example, from Meta, from Lucas Attermore's group, that they try to put together a lot of small models. Yeah. And I think called branch them, merge them, something. And to really put together, starting from a lot of small models, put them together to actually make a larger models. I actually think those approaches are still very promising. This is what I heard, but I cannot really comment on that. Yeah.
Okay, thank you.
I think we can take one from there.
Hi, Danqi. Thanks for a wonderful talk. I'm a professor in SCTU, and my question is more about the pre-training side of the small language model. You mentioned that, well, we have limited limited budget in academic computing. And you also mentioned that there's open source data set like Red Pajama, which is still out of the reach of academia, right? So do you think it's impossible for the academia to converge to a test bed of small language model pre-training? And if so, what do you think is the proper size of the model parameter and the proper size of data set?
Yeah, thanks for the question. I think I actually answered the question in the talk. So I'm really a big fan of this datacom LLM competition. So they have like a different size of the level of the competition. And the second level of competition is basically training the 1 billion models on 30 billion tokens. And they also showed a very nice scaling curve that basically the rankings of between data sets can still be preserved when you scale up. So that's basically the suggestions I would make. So basically training 1 billion models on the 30 billion tokens. Also because they have done a lot of the engineer efforts to make the data really, really clean. So it's a really good effort, and they also unify the final evaluation for so basically the idea is that they provide data set, they provide evaluation. All you need to think about is how to change the data set to actually achieve better performance on their evals. So this is basically my recommendation.
Okay, thanks.
Take a question from over there.
Oh, here. Hi, Danqi. Very nice to see you. Manos from Omi.ai. First of all, I really agree with you. Unlike the comment that was made previously that we should not leave it to the big companies to do the training. Academia has a big role to play. So that's why I was very excited about your presentation. But I wonder and fully agree that we need more GPUs for academia and academic research. But until we get there, what is a good way to help academia with limited compute figure out when they're making a positive contribution? I think was already mentioned a little bit in the previous questions, but as you mentioned, there's things like data comp. I wonder, as opposed to academia trying to create a 1 billion or 3 billion model that competes with the llama or whatever equivalent size, could we say that, no, the goal is to have much more, like data comp, much more limited budget, much more limited this, and we set the baseline, and then we just evaluate ideas about how much are they pushing the state of the art, based on that very limited budget. And maybe again, we don't worry so much about outcompeting llama and all these models, but at least we find on this limited setup what is moving the needle, and perhaps do more research on, as you said before, what is the thing that will translate at a bigger scale and will lead to a good improvement. I wonder actually if we're missing a lot of the necessary understanding about what things will scale up. What contributions at the small scale will scale up well at the bigger one. And maybe that's the things that we need to do to democratize and make it easier for academia to figure out when they're contributing positively.
Sure, thank you. I agree with you. Sorry, what's exactly the question here?
Yeah, so the question would be, I wonder again, do you think that maybe doing more research in understanding what improvements that happen at small scale would translate well at a larger scale? What are the best ways that even academia has limited compute, they would be able to know whether they're contributing to things that would translate to improvements, even at bigger scale when you train with all the trillion tokens? And
I understand. Thanks for the question. The first part is how do we know whether small scale can translate into larger settings? So it really depends on setting. For example, we really need to get a lot of evidence to really understand whether small setting can transfer or not. So for the data part, the pre-training data part I talk about, people have already tried to scale this to larger settings and see whether the data, the quality still matters or not. And another area that I don't really work on too much, but I have colleagues working on is the basic model architecture. So right now, here the standard practice is training 1 billion models on 100 billion tokens. If people believe that if you can really, the model architecture change can really make a difference at this scale, and a lot of people, industry people are trying to scale up these models, so likely there is a hope. Regarding whether the academic work can really make an impact, in the larger scale, honestly, this I don't have answers. This is something I've been confused over the years. But a couple of things I really believe is first, if we can still release these models, people actually still use these models. So I think that's one kind of impact. Second, I want to see like write more research papers and see whether people can actually build on top of these kind of research papers. If any of the industry, larger scale efforts can really use this, the techniques that we developed, that's definitely like one thing that I would bet on. Yeah.
Fully agree with you. Thank you, Danqi.
Thank you.
Okay, in the interest of time, we'll take one last question from this side, and you're welcome to come after this to have more conversation with the speaker.
Okay, hi, Danqi. Thanks you for your very nice talk. And I'm a student from Peking University and Microsoft Research Asia. I'm focusing on data-centric AI and multimodality. My question is, I wonder, is there any shared pattern between post-training data and pre-training data, and how to transfer my post-training data findings to pre-trained data? Thank you.
That's a good question. I would say pre-training data, right now we talk about is still more unlabeled data, right? Post-training data is more like annotated data, either instruction tuning data or preference data. But I still think that there are some like ideas that can be shared between the First, I think right now there is actually a blurred boundary between pre-training and post-training. People start to use some kind of post-training data also in the later stages of pre-training. So right now I see the boundary between the two has become more blurred. Second, in terms of research ideas, I do see like there are some ideas that can be shared between the pre-training and post-training. For example, last year we had a paper I didn't talk about in the talk called LESS, basically using the influence formulation to select the instruction tuning data sets during the post-training stage. And I have seen people actually pick up this idea and try to use some form of the influence formulation to help select data during the pre-training stage. So I would say these kind of ideas would still shared between the two.
Okay. Thank you for your talk.
Okay, thanks everyone. We're ready to wrap up the morning session, and let's give the speaker another round of applause. Thanks.
Thank you so much.